Alright, so the Bohr model of the atom, I just described it at the end there. So the only time that there's any light coming from the atom is when the electron in an allowed orbit switches to another allowed orbit. And actually, that's why each atom has its own unique spectrum, because the electrons are all in different energy levels for different atoms. So hydrogen being the simplest, we're going to talk about that first. So this is, okay, so let me explain what an electron volt is, and well, I'll do that in just a minute. So this is just basically showing all these different lines in the spectra of hydrogen. So that these are the typical 4 lines, depending on what type of, you might not be able to see the violet, this second violet one. At any rate, the energy is, for an electron, is negative 13.6 electron volts. I'll get into where that unit comes from, divided by whatever the state of the electron is, the quantum state, the energy quantum state. So the energy quantum state for what's called the ground state traditionally is n equals 1. Then there's an excited state called n equals 2. Then there's another excited state, n equals 3, and n equals 4, and up to infinity. N is any integer. Okay, so it turns out that the Balmer's, this is actually the Balmer series, the 4 lines. Like I said, it's kind of hard to see this last one if you don't have really good equipment. But these occur, and there's very specific frequencies. There's the aqua one, there's one of the violet ones, there's another violet one, or very specific wavelengths, right? It's usually the wavelength that we measure. So what Bohr said is when the electron makes a transition from a higher state to a lower state, a photon will be emitted, and the photon will have energy, h times f, which we already know, and it's really the energy in the higher state that the electron was in minus the energy in the lower state. So all these, notice for the Balmer series, all these are jumping from a higher state, higher than n equals 2, so like n equals 3 to n equals 2, that's the red line, n equals 4 to n equals 2, that's the aqua line, and then there's the first violet one, or deep blue, n equals 5 to n equals 2, and then there's the n equals 6 to n equals 2. So this is the spectra of hydrogen, and this is, remember, these lines had been measured for almost more than 50 years, or around 50 years, when Bohr comes along in 1913 and comes up with an actual explanation for why they are the colors that they are. And so this gives us a deeper insight into how the atom works. And really, what's taking place here is there's an interaction between light and what is going on with the electron. When the electron's in a higher state and jumps down to a lower state, it emits a photon. And then the opposite is true. It doesn't really talk about that here, but if an electron is in a lower state and a photon of light comes in, but it has to be just the right color, what happens is that photon gets absorbed by the electron, and the electron now jumps to a higher state. But it has to be, the photon coming in has to be exactly equal to the energy difference, right? Exactly like this. All right, so I'm going to do some examples. Let's see. Here, let me go back. I'm going to do some examples with the Bohr model. Let me explain where electron volts come from, and all right, so first of all, if we take 1 volt and we multiply that times the charge of 1 electron, so that's times the charge of a single electron, Q. Well, it turns out, remember this, I don't know if you remember this equation from chapter 6, that work is charge times voltage. That's if you're moving a charge across a certain voltage, then you get energy, basically, or work, which is the changing energy. Work is the process of changing energy. So if I multiply 1 volt times the charge Q of 1 electron, well, let me be clear about that. So 1 volt times the charge of a single electron. That's what we call an electron volt. So that's 1 electron volt. Okay, so that's the way that we write it, and it's, you just say electron volt. And so that turns out to be 1 volt times the charge, and we know the charge of an electron, right? So it's 1 volt times, and I'll put the number in, 1.6 times 10 to the minus 19th. And remember, this is coulombs, but now we have volts times coulombs, and this becomes joules. Okay, because volts times coulombs, according to this equation, volts times coulombs is in joules. So this is a conversion factor that we're going to use. So 1 electron volt, it just turns out to be much more convenient to use electron volts when you're talking about atoms and molecules than to use joules. Okay, so 1 electron volt is 1 times 1.6 times 10 to the minus 19th. So it's 1.6 times 10 to the minus 19th. And it's now, instead of volts times coulombs, it's joules, right? Because that's what a volt times a coulomb is. So this is the conversion factor. This is the thing that we will use over and over again, especially with the Bohr model of the atom. Okay, so, alright, so I just wanted to get a fresh screen. So 1 electron volt is the equivalent of 1.6 times 10 to the minus 19th joules. So that's our conversion factor. Now, what Bohr said is that the energy in the nth state for an electron, so E sub n, is equal to, and n is equal to 1, 2, 3, all the way up to infinity, it's just a whole number, is equal to negative 13.6 electron volts divided by n squared. Okay, so for example, if the energy of the electron is in the ground state, E1, that's pretty easy. The energy in the ground state is negative 13.6 electron volts, right, divided by 1 squared. Of course, so it's just negative 13.6. By the way, the negative here is not because the electron is negative in charge. It has nothing to do with charge. The negative is more about the electron being kind of in a well. It's already below the surface. So if you have like the surface of the well and you want to get out of the well, this would be like the bottom of the well at negative 13.6 13.6 electron volts. That's at the bottom of the well, and so it takes positive 13.6 just to get out, just for that ground state electron to leave the atom and just be free of the hydrogen atom. It takes positive, you'd have to add 13.6 electron volts. Okay, so that's the negative part of this. Alright, so let's say we had that, and there was an electron in a higher state. Let's go with the, I don't know, how about something simple like n equals 4. Okay, just to give you a sense of how this works. So it's going to be negative 13.6 electron volts divided by 4 squared. Remember, that's how Bohr teaches us to figure out the energy of an electron. So it's always negative 13.6 electron volts divided by n squared. All right, so I'm going to do a full example here. Oops, I guess I should pull. So when I do this, this turns out to be 0.85. Come on, 85 electron volts. So the energy in the first state, in the n equals 1 state, is 13.6. The energy in the fourth state, oh, and this is negative. I forgot to put the negative in there. All right, so is negative 0.85. So let's draw a little picture to imagine what's going on. So we have, this is the n equals 4. So the electron is right here, and it's not jumping down. You know, then there's the n equals 3, and so on, right? There's the n equals 2, and then there's, you know, the n equals 1. N equals 1. And so what the electron is doing is it's jumping from the n equals 4 in this particular situation down to the n equals 1. And when it does so, it's going to emit a photon. Okay, so a photon of light. We're going to get a photon. And what the Bohr model does is it will tell us what the the Bohr model will tell us the frequency of light, or the wavelength, either one, when the electron jumps from the n equals 4 to the n equals 1. So we're going to calculate that right now. All right, and so the energy. Oops, I need a new screen. So we had E1 was negative 13.6 electron volts. And we had E4, the energy for the electron in the fourth quantum state was negative 0.85 electron volts. All right, so now we're going to complete this, yeah. All right, so we're going to complete this. We had the electron in the ground state, the E1 state. Whoops, that's 1. It's supposed to be a 1. And the electron in the fourth state, E4. So that's negative 0.85 electron volts. And so what Bohr said is the Planck's constant times the frequency is going to equal, so that's the energy of the photon, is going to be the energy in the higher state minus the energy in the lower state. So in our case here, this is going to be E4, that's the higher state, minus E1. Okay? Now, okay, so let's put the numbers in and we'll get an answer. All right, so I put the numbers in, and I just want you to notice the answer, the difference in the E high minus E low is always positive, as it is here, and so it's the higher state is a smaller number, and you're subtracting a negative. So minus a negative 13 gives us plus. Okay, so it's 13.6 electron volts minus 0.85, and so the answer is 12.75 electron volts. And so that's what the energy is. And what you do now is to figure out what the frequency is. See, the frequency is going to equal this difference divided by Planck's constant. But see, Planck's constant, if you remember, here I'll write it up here. Planck's constant H is 6.63. This is from chapter 7 times 10 to the minus 34th joules seconds to joules times seconds. So what we need to do is convert the 12.75 from electron volts now. This is the point where you have to do that